Good morning, my dear students. So today we are going to cover the fifth unit from the material technology subject. First, so you should know what is the fifth model. So mechanical properties and testing. What is mechanical property? Generally, everybody knows. So mechanical properties means like hardness, strength, tensile strength, compressive strength. So how they are declaring compressive strength and tensile strength. So mainly depends on the plastic deformation and sleep types of plastic deformation, sleep tuning, and type of fracture. This type of fracture and plastic deformation vary from the material to material. What is material? What are the materials available? We know FCC material, BCC, HCP. HCP is harder material than the BCC and FCC. FCC is softer than the other material. This is also small modification will be there. Don't worry about small modification. So now I would like to explain what is slip and what is tuning. When will it happen? If you have any material without applying any force and any stress, nothing will happen. But if you are applying any external force, that time what will happen? You can see. So where from the load and force act during service, like structure, machine, tools, etc. So I'm taking the day to life, how we are using the load and forces. If you are seeing the car structure, a car body, or bus body, or lorry body, just body, nothing else. When you're fitting the all the parts, small load and force will act. That time how our material should react. So our material should withstand the small external force or external load wherever the place, like machining. While doing the machining, so you got to hold the sample. You got to tight, otherwise it will be misplaced or cannot able to get the proper size, shape, especially in the lathe machine. So if you are while tightening or while removing your material get damaged due to the external force, what will happen? It should not happen. If it's happened, so your shape of the your material will be changed. So you cannot use that. So you are holding material, and where what you are going to hold, that material should withstand some external force or external load, including the tools. So if your tool is hard, say for example, if you take titanium, titanium is a very hard material. So if you want to do the machining, so you have to take the harder material for the removing the any remaining or machining the titanium. So that time you are applying the external load and forces. That force also your tool should accept. Otherwise, tool will break and you will get more loss. During the process, during the rolling, forging, casting, welding process. Say for example, welding process. If you take the two sheet, we'll take two plates, two different plates, or similar or dissimilar material. So you have to hold, you have to tighten properly. I would like to explain by my experience in my lab. We have 5-axis welding machine, 3-axis welding machine, R1 resistor welding machine. See, welding strength and proper welding is mostly depends on the how you are fitting in the machine. The sample fitting is the most important thing. Then the other things, power go on, power supply coming and going, and the other external forces is secondary. First, how properly you are applying, that is the important criteria for your welding process. So that time also some external forces and load will act. So our system should not affect. And what are the happenings? No changes in shape, changes in shape, and breaking into the piece. While doing the welding, if you are applying more force to tight, what will happen? It may change the shape. Or if it's the perfect fitness, so there is no changes. Breaking into the piece. If you are tighten very high force, maybe your nut and bolt, and even while doing the welding process also it will break easily. That is also possibilities high. So the happening in terms of mechanics, there are different mechanisms there. No deformation, and we need elastic deformation. Say for example, if you take rubber band, so you can play. If you leave it back, it will come to the original position without any failure. That is no deformation we can call on elastic deformation. But you take any aluminum wire and you play with aluminum wire. Aluminum wire, and why I am telling aluminum wire? Because aluminum is a soft material than the other material. Even copper also you can play. But aluminum wire while playing you can able to see the deformation. But once if you leave it, it never come back to the original position. That is called as elastic deformation. But the in between, like elastic to plastic deformation, that region is called as yield point, transition point also they will tell. But generally here you have to tell yield point. So you will keep on applying the force and playing with your wire. Certain case it will reach the excessive elastic, sorry, excessive plastic region. So again if you are playing, it will break due to the fraction. So these are the three steps, like yield point to high plastic deformation and fracture. This all three will come under the failure nature. Are they desirable? No deformation means generally they will use for the structure application. Structure means part, body, car body, bus, automobile body, or anything. Structure. The elastic deformation generally they will use for spring application. You can able to see the shock absorbing bus, car, even your scooty or bike. So every time whenever you are going up and down, that shock absorber act as a springs act as a shock absorber. And plastic deformation, metal working application like stenting. So plastic deformation means nothing but it's a permanent deformation. It never come back to the original position. So most of the time, while doing heat treatment, so your material undergo the high plastic deformation. It change the uh, strength and hardness. That strength and hardness also depends on the how you are doing the cooling rate, like fast cooling or slow cooling. That is depends. And this is generally heat treatment is generally for the strengthening and hardening process. That's why they mentioned. And plastic deformation and fracture, when it happens, these two combinations generally happen in the machining process as well as testing process. If you take the machining process, like if you want to take the like 10 mm rod you have, like titanium, you want to remove the 4 mm from the 10. So you want final shape of the rod is 6 mm. So that time you have to apply the CT machine as well as fracture mean you have to remove the material. After that only you will get the 6 mm pin from the 10 ampere. And testing. See, for example, if you want to know the material behavior like tens, so you have to take aluminum material and then make the standard tensile test, a sample piece, and you have to do the test until getting the fracture. So here also the plastic deformation and fracture is taking place due to the plastic deformation only, or initiation of the plastic deformation, the fracture is taking place. So what is slip system? Prepared planes of the dislocation movement. Generally they will call this. You can able to see in the slip planes. And prepared crystallography direction. So this is our plane. So if you are applying the force here, so in this direction only, this direction is generally they will call as, this plane is generally called as slip plane, and this direction is called as slip direction. And slip direction and slip plane, so both they will call as slip system. I already told you that material like FCC, BCC, and HCP having different slip system. If any one material should undergo the plastic deformation, that material should have minimum 5 slip system. If you want to deform or plastically deform easily, which material having more than 5 slip system, that material will undergo the high plastic deformation very fast than the other material. See, for example, HCP having only 3 slip system and BCC having 12, approximately 12, and FCC having 48 slip system. That is also approximately. Okay, it means like if you see the FCC, what are the material will be there? Aluminum, copper, tin, and all will come. And BCC, alpha iron material, all the steel, cast irons will come under the BCC. HCP, titanium, and magnesium. So titanium, magnesium, if you want, why titanium is, I already told you why titanium having high plastic deformation. Sorry, you cannot able to do machining easily because it never undergo the high plastic deformation. Because the slip system only 3. If you want to do that any machining or deformation, machining means nothing but last slide we discussed. Machining means nothing but is a plastic deformation plus fracture should take place. If both is not take place, we cannot able to do the machining. So when that high plastic deformation and fracture will take place, that material should have high slip system like VCC and FCC having high slip system, so you can able to get easily wear out fast fracture due to the fracture. But if we take like titanium, HCP material having only 3 slip systems, so high plastic deformation is taking place. Possibility is very less. So this is the reason that material will go for aerospace application. And the more number of slip system indicate that the material is ductile. If material is ductile, see for example, FCC material, most of the material is ductile. It never fractures, it will elongate more. The ductile properties more. A normal number of slip system less than 5 term as the ductile material. So most of the BCC material are ductile in the nature. Because BCC having, a number of slip system greater than 5 terms as the ductile material. Ductile means it will easily fracture. So most of the BCC material come under the ductile in the nature. And the FCC, most of the FCC material come under the ductile material. FCC also having a ductile property, but strength wise it will be less. And mechanism of plastic deformation in metal. First we'll see the slip. So two dominant mechanisms of plastic deformation, namely slip and tuning. Slip is the prominent mechanism of plastic deformation in metal. It involves sliding up blocks of crystal over one another along definite crystallographic plane called as slip plane. So this is one plane, and another plane is there like that. When you are applying any force, the blast force, if you apply force, what will happen? It automatically plastically deforms. So it will involve the sliding of blocks. See, this is one block, this is one block, one. That arrangement you have to assume. So that block of crystal over one another along definite crystallographic planes is generally called as slip planes. So it is analogous to a deck of cards. Like if you take playing cards, they will keep all the cards in that manner and arrange it. And if you touch one, means if you touch like that one card, it will fall down in such a manner. You can able to see steps like that. Only slip will appear when you are seeing the microscope. Okay, when it's pushed from the one end to another, that card I told. So slip occur when shear stress applied exceed a critical value. If you are applying the critical value only, that slip will take place. So now you can see the tuning. The portion of crystal takes up on oriented that is related to the orientation of rest of untuned lattice in the definite. That's symmetrical way. The tuned portion of the crystal is mirror image of the parent crystal, and plane of symmetry is generally called as tuning place. See, first slip case, you can able to see that chord. If you arrange the chord in such a manner, once if you push one side and it will fall down, you can able to see the slip plane how will be there in the microscope. But here, if you see the like that tuning, if you see this face and mirror of the opposite face, you can able to see in the microscope. It means a tune happened. The plane of the symmetry is generally called as tuning, but the tuning portion of the crystal is a mirror image of the parent. So whatever the fracture has happened, that opposite also to look like similar. But here ring is there, forget it. But fingers, you assume like that. Can able to see the one mirror of the another. That is called as tuning. See here. This is the arrangement of the undeformed crystal. When you are applying the force here, so after slip, that crystal is moving towards the opposite side. This is slip. Here there is no missing atom or anything, but if you apply the different force in the different angle, this atom and other set of the atom will be missing. So at the time you can able to see the mirror of these will be this. You can have seen it, 3 row. You see from the top to bottom, this will be the mirror of this. This will be you have to assume. And slipping the single crystal and resolving the applied stress onto the slip system. Dislocation move in the particular slip system in response to shear stress applied. So applied shear stress is the resolve onto the slip system. Generally resolved shear stress, RSS they will tell, which is required to produce the plastic. If you cross the RSS, resolved shear stress only, it will undergo the high plastic deformation. If you are not reaching that RSS level, it will be there in the elastic region. So it means you can able to come back to the original position. And CRSS, they will tell the critical resolved shear stress. Once if you reach the critical resolved shear stress, you cannot able to come back. Permanent failure, or if you change the shape from the one shape to another, there is no chance of getting back to the original position. But there are different processes that is Schmidt law is telling can able to change the original position. See, this is an example for tensile stress. So we are applying force from this side and material will get deform the center such a way, not in the circle of center, but in this way. This is the slip direction, this is the slip plane, and this is the area of the plane. So area of the slip plane generally they will call area divided by cos theta can say. Load acting on the slip plane generally applying the force into cos lambda. You can able to see the what is lambda position. This is the from the center of force to the plane. This angle is generally beta and the slip direction to the force. This is called as the lambda. Okay, through that resolve shear stress you can able to calculate like total force what you are applying and cos lambda and the area divided by cos theta. If you see here, finally you will get the resolve shear stress. So schematic law is also telling the resolve shear stress divided by your normal stress equal to cos theta. And you can cos lambda and cos theta equal to m. M is schematic factor. So CRSS you can able to calculate using the yield stress and cos theta and cos lambda and maximum value will get the critical resolve shear stress. And if you want to know the yield stress, you can use this formula you can get. Okay, and slip will be occur first slip system oriented close to this angle only, like theta and lambda should be 45 degrees Celsius with respect to applied stress. This mainly depends on the composition and temperature. Composition of what? Composition of your material. If your material is FTC or BCC HCP, that is matter, and you are doing in the ambient condition or high temperature environment, that is also matter for the process. So if you see the slip in a single crystal, this is very interesting. So here, this is the direction of force. So this is slip plane. This is the pink color is the slip plane, and this is the direction of the thing. And where you took here, this is only one weld sample, zinc weld sample. From there, you can able to see the slip band. You can able to observe. This is like microscopic image. From this band, you can able to link with this one. So deformation of tuning. Whenever the slip is not possible, tuning will take place and create the deformation portion grain which is just a mirror image of the rest of the parallel grain. So you can see here, generally only these lines, this parallel line only will be there. If you are applying the force, external force due to the not taking the slip, so you can able to see the another line of bottom. It's like it's the mirror of this one. That's why it look like V shape. This mirror is this. This mirror is this. This mirror is this. This is why this is the reason it's called the tuning. If you see the poly structure, how neatly the stress and tune follows arrangement. But here if you see the unpolished surface, so structure will be the irregular. There are two types of tunes available. One is mechanical tune. This mechanical tune happen in the BCC and XP material like steel, most of all the steel material, magnesium, titanium, manganese, and all for the mechanical tune. Annealing tunes like BCC, FCC material like copper, aluminum, beta, iron material come under this type. So what is the difference between slip and tuning? Slip is nothing but orientation across the slip plane is same, but in tune, orientation across the tune plane is different, and atomic movement are equal to the atomic distance. Here, it's totally different, and atomic movements are lesser than the atomic distance, and atoms are moving in only one plane. But here atoms are moving the all the plane in the region of tuning and take place in the millisecond, very fast. It takes place in the less than microsecond. This is the reason. Don't think this tuning and sleeping will take like long time. 1 second also it will be very very fast. Once we apply the force or the external load, immediately the reaction will take place and take place at the low strain rate, sleep, but take place at the high strain rate, tuning is take place, and no sound is created when you are in sleep process. But tuning process, some sound will come, click sound, like tin crack. When you are taking the Coke tin bottle, sorry, tin can, after use, you will crash, that also sound will come, that sound will. So it means tuning take place. I hope you guys are enjoying and thank you very much for your kind attention.